In this lesson, we're going to take a look at some problem-solving techniques and strategies and a couple of example problems for projectiles. The big idea here is that we want to be able to predict where a projectile will be at any time during its flight. As we talked about last time, we know that a projectile can be looked at in both the x direction and the y direction, and that as we do that, we can sort of simplify what we understand about it. We need to be able to tell all these variables apart though, right? What is x final, x initial, vx, etc., the y's and the x subscript. So there's a lot of them. And so let's go through a quick look at that. So if you imagine a projectile being launched from the origin, we have the positive y up, the positive x to the right, and we've sort of highlighted a couple of points, 1, 2, 3, and 4, as we go along. And so we could ask ourselves, well, what is the x, the y, and the x and y position, the x and y velocity, and the acceleration in the x and y at each of these points? Now we can go through them one at a time. At the position 1, we have an x position that is to the right, so positive, a y position that is to the right, so is up, so positive, vertical velocity and a horizontal velocity in the positive direction. The x component of acceleration is always 0 because it's constant velocity, and the y component is always down or negative. If we go to point 2, right, we are still in the positive area for position. The x component of velocity is still positive, but here at the peak of the parabola, the y component of velocity is 0 for an instant. The x component of acceleration is still 0, and the y component is still downward or negative. As we start to descend, the x component and y component of position still are positive. The x component of velocity still positive, that doesn't change. The y component of velocity is now negative, it's moving downward. The x component of acceleration is still 0, and the y component is still negative because of little g. For the very last one, we're still positive in the x direction. We've now dropped below the origin in y, so it's now a negative position. X velocity is still positive and constant. Y velocity is negative and gotten bigger and bigger. X component of acceleration is still 0, and the y component is still down for little g, or negative. So what variable appears on both axes here that we can use in multiple situations? Well, that is time. So it turns out that time is the key to linking what you know in the x direction and what you know in the y direction. If you can find time from one of them, you can use that same time information in the other, which ends up being really helpful. Right? When we problem solve here, we're still going to be doing the same thing we've done in our kinematics problem solving. Make a prediction, draw a sketch with origin and positive directions, write down the knowns, unknowns, and what you want, select the right equation, isolate the variable, plug in the data with units and signs, calculate, and then check your answer. If we look at all of these variables here, of which there are a lot, time, angle, little g, right, are pretty straightforward. The rest have these, subscripts that tell you what they mean. And so we basically doubled the variables of position and velocity to initial and final positions in both the x and y, initial and final velocities in both the x and the y. And we have total initial velocity and total final velocity right here. And for those, we need the angle to completely specify them. The big tip here is to separate your x and y information, literally split the page, put them on opposite sides of a line or something to write down everything and keep track of it. So here's an example. If we start with the projectile at the origin, what we would call 0, and we call up positive y and to the right positive x. That's pretty standard. Then we have a starting place where we know what our zeros are. And this is usually kind of our convention. If the projectile is launched horizontally, the equations get really simple. We just have x final equals vxt, and y final is 1/2 gt squared as it falls down. Vy final is gt, and vy final squared is 2gy final. That's, again, with the origin at its initial position and 0 angle. If we launch it at an angle, though, we have to find components, the x and the y components of velocity. And for that, you need the initial velocity and the angle, or sometimes we have other information we use to get to that point. So how do we solve these problems? Well, the solution strategy is usually a two-step process. To find the variable you want, you usually need to solve for something not given, which is often the time in either the x or the y, and then translate that over to the other side. For example, and this is an example that Ms. Kiltz also went through in another video. You can see her writing it out and sketching it, so you don't necessarily have to watch this part. But if a movie stuntman is to run across a rooftop, then horizontally off of it, to land on the next roof, before they attempt the jump, they wisely ask you to determine whether it's safe. Can they make this jump if their maximum rooftop speed is 4.5 meters per second? I am going to pause this recording. Here's an example problem of horizontal projectile motion. Ms. Kiltz also solved this with pen and paper, so if you prefer that method, go for it. But the movie stuntman is going to run from one rooftop to the other, at least attempt, and we want to know if that is safe. We have some given information here. And the first thing really you want to do after kind of diagramming it, and here we already have the diagram, is think about what is our wanted variable? What are we trying to find? There's a couple different ways to solve this, but I would say, do they make it is our big question. And the real question is, where do they end up, x final? Do they get all the way across to the next roof once they've fallen? Would be the way I would approach this problem. So to set this up, we start with our x and y axis information. If we have x positive to the right, y positive up, we have sort of this path that we may or may not make it across. What do we want? What do we know? What are we not given? Well, we want the x final. We know the x velocity. We're not given time. We have an equation that requires time. We only have one equation for horizontal projectile motion in the x direction. So we're going to have to find that time. So we go over to the y-axis, and we start with what we want and what we know. Well, we know that we want the time. We know the y final. We know the initial y velocity. Also can call the initial position 0. And we can use y final equals 1/2 gt squared, solve it for time, plug in our values with units, and we get about 0.98 seconds, about a second. We would have gotten one, close to one, regardless of how we did it. Then we take that time and we plug it back in to the x final equation, and we find out that the stuntman will have gone 4.4 meters in the x direction as they fell. And that is less than the 6.2 required to make the jump. So we would say, don't try this jump. Maybe use a trampoline or something. Another example we could do is one where we are firing something at an angle over level ground, right? Here we are firing 100 meter per second projectile at an angle of 30 degrees, and we want to know how far away it lands. Well, first off, we could do a quick estimate. This is a 30, 60, 90 triangle, which means the vertical component of the velocity, or the y component, initially is going to be about 50 meters per second. That means it'll take 5 seconds to go up and 5 seconds to come down, about 10 seconds. And then 10 seconds times, about 80 meters per second horizontally will give us about 800 meters or something like that, 870, right? Once we find those components. So we can guess that it'll be somewhere between 800 and 900 meters where it lands. Now, we can do the actual calculation of this, right, by taking the x-axis, what we want to know. Again, we're looking for time because we don't have it. But in the y direction, we know everything we need to solve for time, about 10.2 seconds. We can plug that back into the equation. We find out that it is exactly 884 meters. We're using 9.8 as the value. So rehashing the big idea here, the big idea with projectiles, with projectile motion is that we have x-axis motion, which is constant velocity motion, y-axis motion, which is free fall, and that we can link the x and y motion, which we're dealing with separately, with the use of time.